In this series, we're building up a small 1-bit computer on the breadboard based around the Motorola MC14500, which is a little 1-bit microprocessor. And so far, I think we've built just about everything that we can. I mean, the breadboard is chock full from top to bottom. There's not really any space on there to expand any further. And in the previous episode, we got a program on there that kind of tested every aspect of the machine, from input to output and to the newly added scratch register. But that program didn't really give us any meaningful output. It was literally meant to just test those pieces. And so what I want to do today is I want to try and get a program onto the machine that does give us meaningful output. So I have an idea about how to get it on there because it's quite a long program. So let's hop over to the bench, take a look at how we're going to get the program onto the machine, and then we'll take a look at what the program actually does. So let's get to it. All right, and here's our breadboard computer, and at first glance it looks like nothing's changed since the previous video, but there's actually been two small changes. The first is that I went through and rewired the output and scratch register LEDs, so now the least significant bit is on the far right and the most significant bit's on the far left. I had those backwards in the previous episode, but now we've fixed that, so it all feels a little more cohesive to me. And the second thing that's changed is that I've added a little toggle switch up here. And this toggle switch is actually interrupting the clock signal that's coming from our NAND gate collection over here. And so it's only affecting the clock signal that is being input into our program counter. When the toggle switch is to the right, it's connected up as if though nothing had changed. But if I change that toggle switch to the left, now the center pin, which is what is outputting the clock signal to the two counter chips here, is hooked up to the left pin. And right now that left pin is hooked up to nothing. So why would I want to do this? Well, instead of explaining it to you, I think it would just be easiest to demonstrate it. We're running so fast that we immediately just hit a halt. So if I hold that down, now we won't halt because I'm holding down the continue button essentially. And we can see that there's a bunch of random data stored into our RAM chip here. Well, that's interesting. It halted with all 8 LEDs lit up there. So we knew that the RAM chip would initialize with random data into it. And if we want to put a program on it, we have to essentially switch this over to programming mode. We'll reset it here. And right now I'm just programming 0 into the RAM chip. All right, so if we change this back over to read mode, you can see that as the clock is cycling through all 256 steps, our RAM chip is just outputting 000. Now, the traditional way that we've been programming it is that we switch this back over to single step mode. We reset it to 0. We set this dip switch to whatever binary instruction word we want. Then we hit the clock to go to the next step. And then we set the dip switch, and then we hit the clock, and we go on and on and on. And it's quite time consuming, so I started thinking about ways to make this programming process faster. And there's a lot of period correct avenues that I'm really interested in going down, but for the time being, I just wanted something quick and easy so I could test out a much more complicated program. And so this was the programming method that I came up with. Let's go ahead and get it plugged in and program in our first step here. Yes, I pulled out an Arduino, and the irony of using an 8-bit microcontroller to program a 1-bit computer that we built on the breadboard that is easily 1,000 times larger is not lost on me, but it's making my life a lot easier for getting complex programs into our little RAM chip here. Now, the way it works is that these 8 wires here are controlled by the I/O pins on the Arduino, and they plug directly into the 8 bits that are our instruction word. And then this yellow wire here plugs into the left pin of the toggle switch. So when the toggle switch is in the right position, the clock comes through as normal. But when the toggle switch is now in the left position, the clock is being supplied by the Arduino through this yellow wire here. And then these 2 jumper wires here are just power and ground. So the Arduino itself is going to get power from the breadboard. So now that we've got all the wires hooked up, let's go ahead and put a program into here. And in order to do that, we need to make sure that the program counter is at 0, and it is. And we need to set our RAM chip to right, which it is. And finally, we have to make sure that the clock is coming from the Arduino. And so this little switch is to the left here. So everything is set up. Let's go ahead and plug in the power and ground to the Arduino here and watch it go to work. That was pretty wild. it happened pretty quick. Now, it could actually program faster than that. I have a pretty hefty delay set in there, so I can kind of see what's happening. But there's no reason that it couldn't go a lot faster. But having said that, it's still really fast. So now we have a program stored in our RAM chip here. So let's turn our programming switch off, and we'll go ahead and get the Arduino out of the way here. All right, so now we have a program stored in here, so let's just send it. Let's just hit go and see what happens. So we'll turn this toggle switch back over to the right, so the clock is coming through as normal from our 555s over here. I'm going to turn the speed way down, and then we will turn the clock on. All right, well, yeah, we're doing something. Oh, hey, we got a bit illuminated in our scratch register down here. Well, there's a lot of stuff going on, so let's just crank the speed up and see what happens. All right, we see some interesting stuff happening with our scratch register down here and our output over here. And if I'm reading this correctly, and I should be because I built the program, it looks like our output is counting up by 1. So this is an increment program. That's what we put into our RAM chip. So it's incrementing by 1. Now, the way it's doing this is that it's taking whatever is stored in the scratch register and adding it to whatever our input is. And right now our input is set to 1. So whatever is in the scratch register is being incremented by this 1 here. But if I change this to, say, 3 by just flipping a toggle switch up here, now we should see it increment by 3. And I'm not fast enough at reading binary to tell you if it's actually doing that, but it looks like it is. So let's reset it and let it go. There's 3, there's 6, there's 9, there's 12. So yeah, it is. It's incrementing by 3. How cool is that? So we've built an increment program for our breadboard computer here. How cool is that? Not only that, we were able to program it in just a flash using the Arduino. So I feel like we may have cheated a little bit, but I mean, the results are amazing, is that we have our breadboard computer doing something awesome. All right, so as awesome as this is, I kind of hit you guys with the end result first. So let's rewind a bit and find out how we got here. And first of all, we got the program onto the breadboard really quickly with the Arduino. So how did we do that? Well, let's take a look at the code. So full disclaimer, I am not a very good programmer. I am a terrible programmer. I tend to brute force things where there's often a much more elegant solution. But essentially what I wanted to have happen was that I wanted to be able to write the 8-bit binary instruction out in the program and then have that automatically be put in. And so in the code here, you can see at the top, we declare some constants. These are just setting up our input-output data pins. And then we declare an array of integers called data. And this is actually the binary instructions that we're going to program into the RAM chip. Now you can see that each one starts with a 0B. That's an indicator to let the system know that it's dealing with binary. And then we have 8 bits after that. And those are our 8-bit instructions. And I put a few notes in there to let us know what each section of binary code is doing. But other than that, it's just a massive string of binary digits here. And you'll notice that in the middle of all this, we get to a spot that says end of program. And it's just a bunch of no operations. And if we follow those no operations for a bit, we come back around and it says set up and add without carry bit 0. And this is just the program copied over again. And that's because we have 256 steps available. And the program only took up about 100 steps, maybe a little less. So I just copied the first 128 steps to the second 128 steps. Since the entire increment program is reliant on the entire program counter looping around, having it twice in the same 256 steps allows me to essentially double the amount of times that the program runs. And we'll go into a bit more detail about what the program is actually doing a little later. But if we scroll all the way down beyond that, we get to the actual meat and potatoes of the program. And in the setup section, we're just setting up the input-output pins on the Arduino for output. And then loop is where it gets interesting. And it's pretty simple. We have a for next loop that counts from 0 to 255. So that's all of the 256 steps that we have available to us to put data into. And the first thing it does is it runs a subroutine called 0. And if we scroll all the way down to the bottom, we can find the 0 subroutine. And all we're doing is we're taking all 8 of the output pins and setting them low. And once all those are set low, we jump back up to the top and we start reading the bits of the data. It takes whatever Y position you're at and then reads the individual bits from 0 to 7, so all 8 of those. And if one of those bits is equal to 1, we set the corresponding pin on the Arduino to high. And then all we need to do is toggle the clock. And so we set the clock to high, we wait 10 milliseconds, then we set the clock to low and we wait 10 milliseconds. And then that's the end of our for next loop. So we go all the way back up to the top, Y goes up by 1, and then it does that again. And then when Y is equal to 255, our for next loop is completely finished, and we go to the next step, which just says while 1. And this is just a pause loop, so that way I know that it's done programming. So as I said, it's a really brute force way of doing it, but it got the job done, and the results speak for themselves. I mean, you can see that we're incrementing with absolutely no problems. So awesome, we figured out how to get programs on there. Now for this program in particular, what on earth is happening? How are we achieving an increment with such limited hardware? Well, let's take a look at the program itself, and we'll step through it one step at a time and see if we can't figure out what's going on here. All right, so at address 00000, we have a no operation. So that's good. So we go to the next step here, and then we've got 0110, and this is an OR with the complement, and this essentially forces a 1 into our result register so that we can then store that 1 into the IEN register and the OEN register. This is the same basic setup that we do pretty much every time we run a program. Now here's where it starts to get interesting, because in order to do an increment, we have to be able to add 2 binary numbers together. But if we remember, the MC14500 has a logic unit, not an arithmetic logic unit. It can only do logic operations. So in order to do binary addition, we kind of have to brute force it, which brute force has kind of become a theme of this build, and I'm not opposed to that. So our first step here is to load, and we load the input from here. Okay, so we're loading a 1 into the result register here. Now the first few steps that we're doing are just a half add. We're not including a carry. So we're only gonna add what is at bit 1 in our input and what is at bit 1 on our scratch register. Now we've got our input loaded into our result register here. So we're gonna AND that with whatever's in the scratch register, which right now is 0. So that's gonna make our result register go to 0. That's what our operation here is, 0011. Now, if we look at a half adder, if we take the 2 inputs and we AND them together, that gives us the carry. Now, I need to store this carry somewhere so that it can be used in the next operation. So I'm going to store that carry at the very last bit here. But because our carry was 0, our very last bit is stored as 0, so we can't see anything there. Now, again, we're going to reload the input back into the result register, so 0001. So now we've got a 1 in our result register, and we're going to XNOR that with whatever's in the scratch register here. Now, if we look at a half adder, it's not an exclusive NOR, it's an exclusive OR. But an exclusive NOR is just an exclusive OR with the output inverted. So if we re-invert the output of an exclusive NOR, we can get the equivalent of an exclusive OR. So the next step here, we XNOR the input with the scratch register, and that turned our result register off. And now we need the inverse of that stored into our scratch register as our first bit. And just so happens that we can use the STOC command for that, which is 1001. And this stores the inverse of whatever's in the result register. So the inverse of 0 is 1. So you can see that we have 1 stored here. So we just did binary addition without actually having a full adder on the board. How cool is that? We forced our way through binary addition. But we only do a binary addition without the carry for the first bit. And this program is set up to be a 5-bit increment program. So for the next 4 bits, we need to do essentially a full add. And this is a lot more difficult. But fortunately, the Motorola MC14500 handbook has an entire chapter dedicated to doing arithmetic functions with this chip. And I'm not going to pretend I know exactly what's going on here, but it's kind of like baking a cake. I don't have to know how to bake a cake. I just have to know how to read the instructions. And so all I did was pretty much just copy what they have written here, and that's how I did a full binary addition. So let's skip a little further ahead in our program here. We'll get up to where we have a little more interesting addition going on here. Okay, now we have some more interesting data stored into our scratch register that should demonstrate the addition a little better. Right, and we've actually circled all the way around back to the beginning of the program. So we're just going to burn through these first 9 steps real quick. So now we did an OR with the complement to store an IEN and OEN. Then load, this is the beginning of our binary addition without carry. There's AND, we're going to store that temporarily, we're going to load again, we're going to XNOR, and then we're going to store the complement of that, and now we're at a no operation. And now we're starting the binary add with carry. All right, and so we have our carry temporarily stored here. So we're going to load that carry into the result register, and so we can see that the carry was 1, so we loaded a 1 into the result register. We're going to XNOR that with whatever is stored in the scratch register, which in this case is 1. And then the next step is we're going to do an XNOR again, only we're doing it with the input. And so we're going to temporarily store that new sum into the scratch register. And I'm going to store it at this second bit here, which is illuminated, but this is just a temporary storage place. Now next, we're going to load the value that's stored in the scratch register back in. So that's here, so that's 1. So we loaded that back in. We're going to OR that with the carry. And since that was a 1, and well, the carry's a 1, our output's going to be 1 there. And so you can see that our result register stored a 1 here. We're going to AND that with the input from here, and that is not 1. So that's a 0. So our result register should turn off. Yeah, okay, so there it went, okay. Now here is where it gets interesting. So we're going to essentially do IEN, which is 1010, with the scratch register at 010. And 010 in this case is this 1 here. So that means that our IEN is actually still working. So the next few steps will actually do something. But if this was a 0, then IEN would have been turned off, and we couldn't put any more input into the chip. And so that essentially creates an if-then statement. We're saying if this bit is 1, then do the next 2 steps. If this bit is 0, then skip the next 2 steps. But because this bit was 1, we're going to do the next 2, which is an OR, and we're ORing with the carry in, which in this case is 1, so we still get a 1 in our result register here. So we know that our IEN is still enabled, that's good. And then we're going to store that new carry back into here. And now the next 2 steps are to just restore the IEN register so that we can continue on with the rest of the program. So that was a binary addition with carry. And so this seems like an incredibly terrible way to do a binary count, considering that we did it with just these 2 little chips up here to count up in binary. But the fact that it's doing actual addition means that this can do math on the fly, and we can program it incredibly quick. So there's a lot of really amazing things happening here. So there we have it. We were able to build a computer that's relatively capable, and we can program it really quickly using the Arduino. So now we can just write programs on the computer, come up with different ideas, and test them out rapidly. How cool is that? We created the coolest 1-bit breadboard computer on the internet. I'm gonna lay claim to that. So there's a lot of different avenues that we can go from here, but in its current state, on this breadboard, it's finished. I have a couple ideas about where I want to go in the future with this, but maybe y'all have some ideas that are infinitely better than what I've got. So if you've enjoyed this series and you want to see more, let me know in the comments below. So I would love to hear your feedback about where you would like to see the next evolution of this project go. But in the meantime, I'm going to keep playing with this because the flashing lights are just hilarious and fun and cool, and it's a surprisingly capable machine. So thank you guys so much for watching, and we'll see you in the next episode.